in the middle is filled in. That's good. Now we have to check at 3. Does it do the same thing at 3? Are y'all with me? Okay. Continuity normally, oh look, if you're sitting there going like, this is just kind of a weird topic, it is kind of a weird topic. And we'll move away from it after this and we'll get back to things that are a little more kind of like grind it out and stuff. So this is your first exposure to continuity. If it seems weird, it's normal. All right, now let's check continuity at 3. So I'm going to rewrite this limit. I'm going to replace this with 3. I'm going to replace this with 3. I'm going to ask myself the same questions. Are these equal? So what is f of 3? 8. So we're going to look at this part right here. We're going to plug in 3 right there. We're going to get 9 minus 1. It's going to be 8. So the right side is 8. I'm going to take the limit as x approaches 3 of the function. Now, which side am I going to come in on? The left side, because f of 3, we were on this function, which means this right part, this far right part, we already know this is right continuous. The question was, is this left continuous? So we're going to be working with that piece. Again, it's the same one, just happened to be the same one, this problem. It's not always going to be the middle one is the one you use in here. It'll depend on, well, what do you think it'll depend on? What's the main thing that's going to depend on? Where that equals is. That's what determines it. Because if this equal would have been up here, then we would have been using this one on this side, and then on this one we would have been using this one. But hey, one problem at a time. All right, so what goes in here? X plus 2, and when you add those together, or when you take the limit on the left side, you get 5. So 5 does not equal 8, and so it is discontinuous at 3. And that's the only place. So f is discontinuous at 3. I'm answering the question. At x equals 3. Yes? Here? Say it again? On this one or the previous one? On this one, no. The limit, what's happening here is that, sorry, I didn't put the sign here. That should have been from the left. I apologize. What we're saying is that as we approach 3, from this side, it's approaching what value? 5, but from this side, it's approaching what? 8. So my picture isn't right. My parabola should have been up here, but I was guessing, right? So but they don't meet up. But here, at 1, they did meet up. Does that clarify? Okay. All right, 205. You all hanging in there?
So basically, we're trying to find things if things are continuous, so that we can find if we can find the limits.
No, we're just trying to analyze.
Just making sure it's all together.
Yeah, I mean, does this graph have a break in it or not? You know, that's really what we're looking at.
That's just it.
But we're using the definition of continuity to do it. And that's going, I know it seems like, because,
I just don't understand the purpose. Like what would be the purpose of trying to find if it's continuous? Why would
got you. Understand. Understood. Let me do another example.
Okay.
This next example is going to show you exactly why we might want to do this. Although you still may have some questions like, why would you want to do that? But let me just present it, okay? Let me present it. What we could have easily done is just plugged in the points and just shown that they didn't match up. But I would have never shown you this, and you need this for what we're about to do. All right, here's a function, another piecewise. Here it comes. I'm making this problem up, so I don't promise a good answer. We might have a nasty answer. Let's say we have ax squared. I'm going to try and keep within the same reason of the other ones in the book. Bx plus 1. If x is less than -1. Let's say we have 4x minus a plus b if -1 is less than or equal to x. Or let's say, yeah, we'll go less than or equal to x, less than 0. And one over x if x is greater than 0.
So there's no equals to?
Yeah, no, I need one of these to be equal. Sorry, thank you. Let's do equals. I can't do equals there. There we go. Let's do it up there. Let's do that.
But does all piecewise functions have to have an equals greater than or?
No, you can have undefined parts of a, but then you would automatically have discontinuities. Hold on a second, though. I really want this to work, so I have to change two things. A couple of things, actually. Hope you don't write in pen. Change this to a 1 and change that to a 1 and make this x squared minus 1 over x minus 1. There. I don't want to go through all the work that's going to be required and it's not work out, so let's do that. All right. We have three pieces to this function, right? We have a parabola, we have a line, and we have a rational function. Now, a and b in the problem right now are constants. I don't know what they are. You don't know what they are, all right? They're just some numbers. The instructions for this problem are to find a and b so that f is continuous on -infinity to infinity. I want you to tell me what a and b would be so that these things, that when I draw this function, I don't have to pick up my pencil. Are you good? You understand what that's saying? All right. Make sure you wrote that down. I'm going to help us out with a little visual here. It's going to take me a minute, but just hang tight. All right, what was the first one there? It was a times x squared minus bx plus 1 hold on just a second. Do a little copy paste here. Next one was 4x minus a plus b. And the last one was x squared minus 1 over x minus 1. Okay, that should do it. I'm sorry to make you sit there. I should have had this ready to go, but I didn't. All right, I should get this here. Whoa. I don't like that. All right, I'm going to try and explain it to you with this picture because I don't want to go and type up stuff for more time or use up more time. We have a parabola, a line, and a rational function, right? I'm going to erase these. And that's what they could look like, all right? That's what they could look like. What we're trying to find is the A and the B that makes this continuous. So if I adjust the A, it's going to have an impact on both the parabola and the line, right? Look at when you wrote it down, both the line and the parabola have A in it, don't they? So as I adjust A, it's going to change the line and the parabola. If I adjust B, it will also change the two, won't it? Yeah? Yes, yes. So what I'm trying to get is this. The parabola is defined to the left of -1. Yes? So here's -1. The parabola is here, like this. Is there an equals on the top one? No. No? So I have an open circle here. The line is defined between -1 and 0. Or 1, yeah, I changed it to 1, didn't I? And there's a dot at -1 and a dot at 1, right? And then the rational function, which I believe is this last one, although that could have been the rational function, it doesn't matter, is from here to here, okay? There we go. Do y'all see that? Those pieces? Yes? I'm trying to figure out if there's a way that I can move them around so that they all line up. Do you see right now the way it was written just a second ago, they didn't line up? I'm trying to tweak A and B to make these line up together. Yeah?
To make both the points line up?
Everything's got to line up. I got to be able to draw the whole thing without picking up my pencil. Is it possible? We're about to find out. Do you think it's possible? We'll see. Do you understand the problem? Now you were asking like where would this apply, right? And I understand that question. Here's where we're trying to model something that acts like parabolic first, and then it becomes linear, and then the last one is a rational function, but it's actually linear. Okay, so you have like, you're modeling behaviors that behave a certain way, but then after a certain point in time they behave different, and then they change. So you're trying to somehow come up with constants to make this a nice function. You can't do this without the concept of continuity. All right, that's geographically, that's geometrically what we're trying to do. All right, where do we need to look in order to make this happen? What do we need?
The equation itself.
You know what?
The equation itself.
Yeah, we have to go back to the function. Are we interested in what's happening on the left or inside the middle or on the right? I mean, where's the only place we're interested in? The -1 and the 1, right? I need two things, right? Two things. First, I need continuity at -1, and then the other thing I need, continuity at x is 1, right? That's what I need. If I have those two things, then this thing should be continuous, because to the left it's a parabola, that's continuous. In the middle it's a line, that's continuous. In the right side it's a rational function, which is continuous. It's just a matter of pasting them together. So let's write down what the definition of continuity at -1 would be. Limit x approaches -1 of the function must be f of -1, right? Now I've erased the function, but I need it. So I'm going to write it down on the side over here. F of x equals, what do I do? ax squared minus bx plus 1? If x was less than or equal, or just less than -1, then it was 4x plus what? Minus what? A plus b. And then this one I remember. This was if we were -1 less than or equal to x less than or equal to 1, and this one was x greater than 1. There we go. All right, so when we set this up for continuity at a point, the right side is just college algebra. You just plug -1 into the function. So which piece are we going to be messing with here? Top, middle, bottom. Middle, right? Middle, because that's equal to -1. So plug -1 in here for x and tell me what you get. -4 minus a plus b. That's what you get, right? Now, the left side is a limit. I need to give myself a little more room. I'm going to move this down just a little bit. -4 plus a minus a plus b. The left side, I'm going to do a limit. Now, which side of -1 am I going to come in on? The left or the right? The left, because we're coming in from this function, right? This function into this function. This function is to the left of this function, right? So I'm going to come in from the left, and I'm going to put it up there. Ax squared minus bx plus 1. And now, just take this limit. Replace your x with -1. What would you get if we replace x with -1? You get a plus b plus 1, right? Equals what? -4 minus a plus b, right? Damn, I didn't want this to happen.
Do you have to solve for one of the variables?
No, but does anyone see what happens to my b's? They can't. I don't want it to be this easy, okay? Because that's not going to happen for you on your homework or your test. So I do have a quick fix if y'all will.
Make one of the
Just change this to a 2b. Change this to 2b. It doesn't do anything except change this to a 2b and change that to a 2b. Is that okay? Is that okay? All right. Now let's try and see what we have here. That's a single equation with two variables, right? You can't solve a single equation with two variables. You can't get an exact answer, right? So I'm going to just hold off on this for a second. Just going to wait. But just remember, I have one equation, two variables, right there. Yeah? Let's walk over to this. I need this to happen too, right? I need that as I approach 1 on the function, I'm equal to f of 1, right? What is f of 1? So we're here in this one. Plug 1 in, and what do you get? 4 minus a plus 2b. And that must equal the limit as x approaches 1 from which side? The right side, because we're at 1 here. That means we need to look at coming in from the right side, which is this function. Right? That's to the right of 1. So I'm going to be coming in from the right. So the function I'm going to use is x squared minus 1 over x minus 1. And if you try this limit, you get 0 over 0. But from homework last class, you could factor, right? Difference of squares on the top. You could get the x minus 1s to cancel. It would leave you with x plus 1. You'd apply the limit, you would get 2. So I'm just going to trust that everyone could do this limit now and get to 2. So you get 2 equals 4 minus a plus 2b, like that. You have a second equation with the same two variables as this one, which in college algebra we called a system of equations, a system of linear equations. Yes?
quick question. For when you first notated with the limit of the fx, is that supposed to have the positive? Is it supposed to be for both sides? Or
This does mean from both sides.
right.
But the fact that we're defined at 1 in the middle equation, right? That means that when we're approaching in that middle piece, Here's 1. Here's negative 1. At 1 we're defined, and that comes from this middle guy. I know that there's a line coming out the side, right? So I already know I'm left continuous. So this means I need full continuity, but the way it's defined, I know I've got half of it already. The question is what's happening out here, right? I need to fit this. Yeah, no, this is supposed to be nothing and then plus. The plus is what tells me which piece of this I'm looking at. Okay? Yep. All right, so we have 2 equations, 2 unknowns. So I'm going to set up a system of equations. The way I'll do that is I will first I'm going to get all my variables on one side here. So how about add a to both sides? I get 2a. And then how about subtracting 2b on both sides? I'll get negative b. And then let's move all the constants to the right. So subtract 1, we get negative 5. That's one equation, isn't it? The other equation, I can do this. How about I just leave these here and move the 4 over? So I get what, negative 2? And then negative a plus 2b. You can do, there's 2 ways to solve this that you hopefully were taught. One of them is called substitution, and the other way is called elimination. Elimination is a more powerful method because it works for 3 equations and 3 unknowns, 4 equations and 4 unknowns. I'm going to use elimination because I think I'm basically there if I use elimination. All I have to do is look at the variables. So this is something where if you're like, what the hell is he talking about right now? Where you just write down elimination, substitution, and you just go to the lab or you come to me like, I didn't know what you were talking about, right? I'm going to make either the A's or the B's go away. And to do that, I'm going to work with the A's. So 2a, to make 2a go away, I would love to have a negative 2a here. So I multiply the bottom equation by 2, all the way across. And I rewrite the whole thing. So I get a new system of equations, 2a minus b equals negative 5. And then distributing through, I get negative 2a plus 4b equals negative 4, like that. And then you can add these equations straight down. And when you do that, the a's go away. You get what? 3b equals negative 9. I couldn't have tried to get even if I tried to make this problem turn out with b being a nice integer like that, I couldn't have done it. This is purely accidental that b is an integer. Okay? Right? B is what? Negative 3. I could have only hoped for it to have done something like that. Now, that's b. What's a? Well, you can get a from either one of these. Right? You just go back and plug b in. So let's go, how about I go to that first equation up there. 2a, I'm taking away b. What's b? Negative 3, and that must equal negative 5. Now, if this is an integer, I'm going to go buy a lottery ticket tonight. 2a plus 3 equals negative, oh my goodness. I'm playing the lotto tonight. Do you realize how difficult it is to make up a problem and have integer answers?
Yeah, because in algebra,
Negative 8, a is negative 4. Wow.
you could make a nice problem statement life in algebra.
What?
It's true.
I save all the hard problems for the test, right? Okay, so I'm going to go back over to this, and I'm going to have the computer graph this for me. I don't even believe that we did this. All right, so I have to change, remember I changed that to a 2b in there?
Yeah.
Got to do that first. I also don't like my plot range, so give me a second to change this. I want to only graph between, let's say, negative 5 and 5. And on my y values, let's go negative 50 to 50. Let's just see if this looks a little better. Yeah, that's a little bit better. See that in there? And I need to do just a little bit more. Negative 10 to negative 1. This one's going to go from negative 1 to 1. And this one's going to go from 1 on. Okay, so I'm cleaning it up a little bit. Those were my pieces. You see my pieces? Yes? I needed to try and get these to all come together. if I move this slider to -4 and I move this slider to -3, they better line up. It's all on the line right now. Okay, so here we go. I don't have to slide it, I can just type it in. A was what? -4? Ooh, that looks like it got worse. What was B? -3. Ah, it works. See that? I was able to paste all three pieces together to make a continuous function. So this is a good, I mean, this problem talks about limits. Limits from which side? You have to understand that. You have to understand how piecewise functions work. You have to solve a system of equations. It's like a big, nice problem, isn't it? Yes.
Now, when we have to solve, when we have a problem like this, can we just plug a system of equations into the calculator?
I do not care in this class how you solve a system of equations.
It's a lot quicker.
Yep. If you were taught how to do it by your calculator, that's fine with me. Because in a Cal 2 class, you'll be solving systems of equations that have 4 or 5 variables, and that by hand would take a long time. So by the time you get to Cal 2, you better have a way to do it on your calculator. You're going to be sitting there taking 30 minutes on the test to do something that's taking other people 5 minutes. So, all right, we have one more thing, and I only have about, what, 11, 12 more minutes? And that is this last topic that involves what's called the intermediate value theorem. If today you already feel like you're going to walk out of here and you're just like, man, Cal 1 is turning into this nightmare now, just do not gauge what Cal 1 is on today's material. Continuity is just a weird topic. We're going to leave it behind, okay? We're going to just leave it behind.
When will we pick it back up again?
No, I mean, continuity is just a very important property of functions, and we have to talk about it. And it is something that we don't talk about anywhere else because to define it, you have to understand the limit. And we just started talking about the limit, right? You can't talk about continuity in college algebra other than to say you can't, you pick up your pencil. So it's, yeah, all right. The intermediate value theorem. This is actually a very powerful theorem, and I'm going to introduce this idea with a problem. Cosine x equals x. And you know what? Let's go x to the 5th. I did that in my other class also. Solve that equation. Now, don't really solve it. Just think about how you would solve it. If you have any ideas, I'd love to hear them. I'm typing it into Wolfram Alpha, all right? I'm going to have Wolfram Alpha solve it for us. And the answer is 0.907550. And there are actually more digits. If I clicked on this and I probably had to pay, like for the pro version of this. But it also has this thing. Can you all see what that is? Squiggly equals, that's approximately. So even Wolfram Alpha, the almighty Wolfram Alpha, is understanding that this is an approximate solution, that they're not going to be able to provide you with the exact answer. All right?
Kind of like pi or e or...
No, because it's kind of worse, because if it were pi or e, they would just write pi or e. This is an approximation. Now, if you need the approximation to be really close, they can probably go out as many digits as you need. They can probably go out like 1,000 digits if you needed that much precision. I mean, for most applications, that would be good enough, right? Like if you're building a set of Legos, right, you're building an airplane out of Legos, like a little toy airplane, right? It's okay if your Legos aren't perfectly pushed into position, right? They can be off a little bit. If you're building a real airplane, you got to have all your tolerances have to be dead on, right? Within a certain precision. So in real world application, we only need this so many places, right? We can only measure so much, right? So at some point, it's good enough. So where's this approximation coming from? Well, I'm going to tell you, and I'm going to try and tell you in 8 minutes, which is going to be difficult. First, let's agree on one thing. We're all not going to be able to solve this. You can never get x by itself. When you try, like if you try and get the x out of the cosine, you come in here with like arc cosine on both sides, inverse cosine. You're like, yeah, I'm going to free it from cosine. But as soon as you do that, what do? You put arc cosine here, arc cosine here. Now you've trapped the x to the fifth on the other side.
What if you take a limit of cosine?
That's still not going to help us solve it though, right? It's not going to help us solve like what x is. But there is a solution according to Wolfram alpha. There is an answer. It's like 0.90775. If you plug that in here and plug that in here, they should be pretty darn close to the same number. Where is it getting that? Well, believe it or not, it is relying on this thing called the intermediate value theorem. And it goes like this. Let's just say that you have a function, all right? Here it is. I have a function. And let's say at a, the function's value is, well, let's just call it f of a. Isn't f of a how high off the ground it would be? And then if I go out here to b, that the height of this off the ground is f of b. The intermediate value theorem states that if you have a continuous function, must be continuous. If I have a continuous function between a and b, so I have to be able to go from here to there without picking up my pencil. Okay, there it is. There's a continuous function. If this is continuous, I must achieve every value between these two. Every intermediate value must be achieved. So let's say, just for the sake of demonstration, that was 1, and let's say up here was 5. Somewhere in there, it has to be 4. So there's somewhere over here, somewhere, I can't tell you where it is, but somewhere in here, I've got to be able to achieve 4. And that holds for every value you could think of between here and here. So what, pi is in there, isn't there? Isn't pi in here? 3.141, right, blah, blah, right? Pi is in there. Somewhere in here, pi is in here. Pi is achieved. Every intermediate value is achieved. You must have continuity for that to work. In my lecture video, I show an example of a function that is not continuous. And so like if this was 5 and this was 1, right? Am I ever going to achieve this value right here? No. So that's why the continuity is so important. All right, so the theorem just says as long as you draw it without picking up your pencil, every y value between the two has to happen somewhere. Now, how is that related to this? Well, let me show you. I'm going to take this equation right here, and I'm going to move everything to one side. All right, there we go. I moved it all to one side. The what? I'm going to, just on this left side, I'm going to call this left side f of x. So I'm defining everyone right now, I'm defining a function f of x equals cosine x minus x to the fifth. All right? There. If I asked you to find the x-intercepts of this function, what would you do? What have you always done when you've been asked to find the x-intercepts of a function? That's the y-intercepts. Set it equal to 0. Wouldn't it? That's what you do? So if I define this function this way, then this equation really corresponds to the x-intercepts of that graph, right? That's what I want. I want the x-intercepts of that graph. That's what this means. Y'all still there? Okay, I'm going to come out here. I'm going to look at this graph for a second. That graph, I'm not going to even try and graph it, but I'm going to just take a wild guess right now. I'm going to plug 0 in. Everybody, plug 0 into that and tell me what you get. You get 1. Cosine of 0 is 1 minus 0 to the 5th power. You get 1. Here we are. 1. All right, now let's plug in 1. I'm taking another wild guess. 1. What's cosine of 1? Someone on their calculator with, oh, careful. You have to be in radian mode. I'll do it even better. Let's do something everyone can do. What's cosine of pi? Make that a pi instead. What's cosine of pi? Cosine of pi minus pi to the 5th. Cosine of pi is -1. Minus pi to the 5th. What can you tell me about this number? Is it positive or is it negative? It's negative. So I know that when I go to pi, I'm down here, right? Somewhere way down there, but I'm down there, right? Is this a continuous function? Is the cosine function continuous? Yes. Is x to the 5th continuous?
Yes.
Yes. When you subtract two continuous functions, it's still continuous. Which means that when I draw the graph, and I, again, don't know what it looks like, I must go from a positive value to a negative value, right? Somewhere in between there, I have to achieve 0, don't I? Somewhere in there. Yeah? So I know that there's an answer in there, don't I? I know that there's an answer. I just don't know where it is. I don't know where it is. I only have a minute and a half. On your homework, what you're asked to do, they give you an equation like this, and they ask you to show that there is a solution to this equation. And what you need to do is you need to do what I did, define it as a function, and you need to pick 2 points. And you need to show that it changes from positive to negative or from negative to positive. If you can show that, then you have shown that a solution exists. You have not found it, but you have shown it exists. All right? Now, what does Wolfram alpha do?
It gives you an answer.
It gives you an answer. Now, what is it doing? Let me show you. And I have 1 minute. This is what Wolfram alpha does. It comes in here and it says, look, I know that I went, it does pick 2 numbers. And it looks to see if it can get a sign change, plus and minus. So it says, good, I know there's a 0 in here. And again, I don't know where this happens. Okay, so I'm guessing, all right? It happens somewhere in here. So Wolfram alpha says, all right, if it happens in here somewhere, let me go halfway, pi over 2. Let me try that. And if it spits out a negative number, again, then it knows that the actual solution is where? Somewhere between 0 and pi over 2, but it's not over here, right? So it cuts that in half again, and it tries that, pi over 4. This time, this would turn out to be positive, and it would say, wait a minute, hold on, I'm going from positive to negative in here. So it cuts that in half, and it keeps doing that thousands and thousands of times per millisecond until your interval gets, right, it keeps on getting bisected. They actually call this the bisection method. And it keeps bisecting these intervals down and down and down, 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 until it gets an interval that's so tiny, right, so small, that if they just take the number right in the middle, they can give you that as the answer. It's close enough. It's not the exact answer. It's close enough, though. And how wide this little interval is pre-programmed into the computer. All right. That's it, right? Do your homework. Make sure you watch the video for next time. I do anticipate a quiz on Thursday. You know we don't have class on Monday. I mean, we don't, but you know that all classes are canceled Monday? Right? Holiday? Okay. Have a good day, everyone. Did Garrett or Muhammad or Joseph? Let's see. How about Joseph? No?
Last name, Joseph?
No, hold on. Is it TC Chelsea?
Just Chelsea.
Chelsea. See, that's complicated.
I know. Literally story of my life.
I bet you get this all the time. Well, a lot of people.
That's my mother.
Your mother, okay. Chelsea.
Chelsea.
See, on the roster, I don't remember seeing a T. It is there. Very creative. Is your mom an artist?
No.
No?
No.
Okay. All right.
Sir, may I ask about
Yeah, let me turn off the video real quick so that we don't get randomness here.